Hello everyone and welcome back to another live recording session. In this session, I want to talk about a strange problem that I had with a script when I was trying to use a stageless payload. And this is one of those things where it's a really simple problem to solve in hindsight, but when you're working on it, if you overlook a couple of things, you can really get lost really quickly. And I want to give a huge shout out to OJ here for pointing me in the right direction for how to solve this. So before we get started, we first have to really understand the difference between a stageless and a staged payload. And here you can see OJ, he's got a great blog post about this that explains the difference. And we can see here that there's two major categories of payloads. So we have the staged payload and we have the stageless payload. And the staged payload is, as OJ says here, probably the one that you're most familiar with. It's a small script with a small stager, and what the stager does is it talks to the server and it pulls in the made payload and it executes it. So a staged payload is usually a small stub, so it's a smaller script, which then calls back and then executes the bigger stage. And so a stageless payload, on the other hand, doesn't include a stager. So it just includes the entire payload that's required. So in this case, for Meterpreter, a stageless payload would include the entire Meterpreter payload, whilst conversely the staged payload, that would just include a small stub that would then download and then later execute the entire Meterpreter stage. So that's the difference between the two. So now let's have a demo of them in action. So now we're on the Linux machine here. Let's use MSF Venom and Metasploit to set up a staged payload, which we can use for our demo. So we can use MSF Venom and we'll specify to create 64-bit shellcode. We'll specify the payload, Windows, x64, Meterpreter, reverse TCP. We'll set the local host, set the local port, and we'll specify that we want some C code. And we can set up the handler here as well. So show options, set the payload. So we want the payload to be the same payload that we just used. Same L host as well. Same port. Check the options and run this. And I'm actually going to execute this again, but this time I'm going to save it to a shared directory that's accessible to both the Windows and the Linux VMs. So let's call this demo.c. And if we take a look at demo.c, we can see what MSF Venom's done. So it's created an unsigned char buffer, and inside the buffer, we have the staged Meterpreter shellcode. So let's jump over to our Windows machine now. And we can set up a script to execute this. So let's start Visual Studio. Let's create a new project. Let's just create an empty project. YouTube demo. So now we have a new project. Let's add a new file. Source.c++, that's fine. Zoom in a bit here. Let's change this to be x64 because that's the kind of shellcode that we created already. And now we can create a simple script here. So let's first set up the main function. And in order to execute that shellcode, we first need to allocate some memory for it. So let's do that. Let's use virtual alloc. Let's include windows.h. And let's take a quick look on MSDN for this function, MSDN virtual alloc. And we can see how to use this function here. Virtual alloc reserves, commits, or changes the state of a region of pages in the virtual address space of the calling process. So we can use this to allocate memory inside of our program. And the expected parameters here are the address, the size, the allocation type, and the protection type. So let's fill those in. Let's pass null as the address, give it the size of the buff, which was the shellcode that was created by MSF Venom. Let's create the memory to commit or reserve. And let's give it the permissions of page, execute, read, write. So this memory permission enables us to write the shellcode to this address, and then we can also execute from here as well. And we also need to include the actual shellcode, and we wrote that to a shared directory, so we can just include that directly like this. And if this allocation was successful, so if it returned an address to us, then we can use memcopy, and we can copy into that address the shellcode and the length of the write. And now that the shellcode's been written to this address, we can execute it directly. Like this. And we don't want the program to exit as soon as this happens, because then we'll lose our shell. So let's just sleep for some time, long enough for this demo. And so again, just to recap what the script is doing, we include the shellcode that was created by MSF Venom. Then we use virtual alloc to allocate some space. We write the shellcode into that space, and then we directly jump to that shellcode and execute it. And then we just have a sleep here to prevent the application from dying. So let's execute this directly now. And Windows has correctly identified this as a virus because it has Meterpreter in it. So let's turn this off again. Keeps turning itself back on. Okay, let's try that again. And now our script is executing, so let's jump back over to our Linux machine. And we can see that we now have a Meterpreter session. We can verify that, get UID, and we have a Meterpreter session on that host. And in the Meterpreter output here, we can also see some of the execution that occurred. The stage was sent across, and then that little stub took that stage and it executed it, following the process that OJ documented on his blog. And so this is working as expected, right? We used MSF Venom, we created some shellcode, then we created a small script to execute that shellcode. So everything was working as expected. And so now let's follow that exact same process, but this time let's create some stageless shellcode. So to create the stageless shellcode, we want to change the payload type like this. And now we can create that shellcode again. We also need to change the payload in Meterpreter. Whoops. Set payload, not use payload. Go options, run. And we can see that there's a significant size difference, right? So when we're using the stageless shellcode, the payload is some 200,000 bytes. And then when we were using the stage shellcode, the payload was only 510 bytes. So there's a significant size difference here. And that's because this stageless version doesn't need to talk on the network to pull in the actual stage. So let's jump back over to Windows now. And now we don't actually have to change this program at all because it's now reading that new version of the file. We're still allocating memory. We'll just allocate more. We still copy over the shellcode and then we execute it. So let's try and run this. And we can see that we end up having an access violation here when we try to execute this. And if we jump back over to the Linux machine, we can see that nothing's happened. So we don't have a shell here. And so now the question is, well, why not? Because this script hasn't changed. This file has changed, it's just a bit bigger, but it's still the same process, right? We're creating the shellcode using MSF Venom, and we've got this little script here to actually perform the execution. And so when I got to this point last time, I tried a whole bunch of different things. So I tried using write process memory instead of memcopy. I tried checking all the error messages with get last error. I tried creating x86 and x64 versions of the binary and of the shellcode from MSF Venom. I also tried different types of payloads. So I did the same thing with Cobalt Strike. So I created the staged and the stageless versions, but had this same strange exception. I also just tried creating EXEs directly. So from MSF Venom, you can create EXE files instead, and that worked perfectly fine. I also tried to debug those EXEs and didn't have any problems there either. And I also tried to verify the memory. So the way that I tried to verify the memory was I tried to do that programmatically. So I didn't want to jump in to the debugger here at this point. So what I tried to do was this. So the assumption here is that at this point, the memcopy's been performed, but we can sort of verify that assumption a little bit. So we need to create a temporary variable here, char pointer temp. Mem. And we need to do this. We need to do this cast because we can't convert a void pointer to something without casting it first. And we're going to need to do that. So let's just iterate over some of the memory that we've written. And we can print that memory out. And to print, we need to include standard IO. And so what this little snippet here is doing is it's taking that memory address, so the address that we've written to, it's iterating over the first 15 bytes at that address, and it's printing them out. So we can execute this and see the difference. So here we can see the bytes that are at that memory address, and we can check that that is accurate. And so here we have the actual shellcode that was created by MSF Venom, and we can see here that this looks right. So we can see 4D, 5A, and so on through to E4. So the memory looks correct. And we can verify this even further. So we can look at more memory and execute this again. And we can again verify this, but this is starting to get a bit tedious checking every byte this way because there's a lot of bytes here that we need to check. And so let's do what OJ recommended, which is what I've been trying to avoid, which is just to use a debugger. So let's compile this, let's build it. Except to make our lives a bit easier, let's just modify the first byte of the shellcode here. So let's change this 4D into a CC, which is just an int3, and this will cause the debugger to break when this int3 is hit. So let's build this now. And let's open up a debugger, x64 debug. And now we can start this program. In the debugger, execute this. And what should happen and what has happened is we've hit our breakpoint. So we can verify this. So here we have the shellcode on the left and the debugger on the right, and we can see CC, CC, 5A, 5A, 41, 41, and so on. So we can change this CC back to, what was it, 4D, I think. And now we can step through the execution here. So let's step through these functions. And it's not important at this point what they're doing. And now we can see what's causing our problems, right? So we've called into this point in memory and it's filled with null bytes. So there's no data here. This is all uninitialized memory, which is a bit suspicious because when we look at the demo.c, what Meterpreter spat out, there are sections which are full of /x 00s. But in general, it's full of data, it's full of bytes because this shellcode is doing something. But then when we look in here, we can see that after some period of time, it's consistent, it's consistent, it's consistent, and then all of a sudden, we're just full of empty memory. A lot of it. So, I mean, what's happened here? Why has this happened? Because when we look at our source, this is quite a simple program, right? We're allocating some memory, we're copying our shellcode into that memory, and then we're executing it. We're not doing anything fancy. And again, this is directly created from MSF Venom with this one exception. We haven't mucked around with this. We haven't changed it. This is just the raw output. So this had me stumped for a while, but if you search for the right thing, Stack Overflow can often give you the right answer. And that's the case here as well. C++, string too big, trailing characters truncated, which is sort of what's happening to us. And we can see an answer here from Captain Oblivious. And he says, the standard does not specify a maximum limit of string literals, but does suggest a minimum size. And he has some quotes here. But eventually, what we get down to is the crux of our problem, which says, if you are using the visual C++ compiler, the maximum size of a string literal is 16,384 bytes. And this limit applies to strings of type char array and wide char arrays. If a string literal consists of parts enclosed in double quotation marks, the preprocessor concatenates the parts into a single string, and for each line concatenated, it adds an extra byte to the total number of bytes. So basically what's happening here is that the compiler is silently truncating our shellcode. It's not telling us that that's happening, or at least I can't see that it's telling me that it's happening, but in the background, that's what it's doing. It's allocating the memory, but then instead of copying the entire shellcode into that point in memory, it's silently truncating it and only writing some of it. So that's pretty annoying, and I spend a lot of time to get to that realization. However, once we know the problem, we can fix it. So we can use Control H here to do a find and replace of this shellcode. And so what we can do is we can replace /x with 0x with comma 0x, replace all. And then we can replace quote comma with nothing, replace all. And then our last replace, Control H again, can replace quote with comma. And lastly, we need to add opening and closing brackets for the array. And get rid of this trailing comma here. And so what we've basically just done with our find and replace is we've changed the shellcode from being a large string to now being a large character array. And while visually to us, it's basically the same thing, the big difference here is that the compiler won't truncate this. Well, the compiler shouldn't truncate this. So let's just check. So on our Linux machine, we still have the multi-handler running, waiting for a connection from the Stageless shellcode. And we now have the Stageless shellcode in a character array, so we shouldn't get truncated. So let's execute this. And we don't get any errors here, so that's a good start. And now if we jump back over, we can see that we now have a Meterpreter session. And we can see that this is a stageless payload because there hasn't been any stager that gets sent over the network. So this is a fairly long story for what is essentially a simple fix, which is to change from a string to a character array. And the fix in itself is quite simple. However, the difficulty, or at least the difficulty that I had when debugging, is making a number of assumptions that weren't correct. So I assumed that memcopy was copying the entire buffer, and I didn't really test this assumption fully until I was challenged on some of the assumptions that I'd made. So in this video, I just wanted to show everybody this problem. I wanted to talk through a little bit of the steps that I took along the way. And I also wanted to admit that I spent well over 5 hours with this problem and potentially would still be looking at it without OJ's direction on where to look to resolve this. So I hope you learned something from this session, but that's it for now, and I'll see you all again next time in the next video.